Hello and welcome to College Algebra for Business. Today we're going to be talking about rational expressions. And what is a rational expression? Well, it has to do with the word ratio, which we also know as fractions and which can appear in different forms. We're going to use algebraic forms. In fact, we are going to be looking at a polynomial over a polynomial. Often, when we are working with fractions of any type, we are interested in expressing it in an even simpler form. So simplifying polynomial ratios is one of the things we're going to be doing today. When dealing with ratios, the one thing we must remember is that the denominator cannot equal 0. But as we look at our denominator here, we don't know what a numeric equivalent to this is because we have a variable. So what we have to do is make sure that when we are communicating this ratio, we identify which values x cannot be. In other words, which values of x would make that denominator 0. Now, how are we going to figure that out? Well, the first thing we need to do is use our rules of factoring polynomials. I'm going to leave the numerator alone for now, and I'm just going to factor the denominator. I have a greatest common factor in that denominator of x. So my denominator can be expressed as x times the quantity x minus 2. Now that I have this factored, the entire denominator is going to be equal to 0 whenever either of those factors, the factor of x equals 0 or the factor of x minus 2 equals 0. So if x equals 0, the denominator will be equal to 0. Therefore, we have to exclude that. X cannot equal 0. And also, if x minus 2 equals 0, we're trying to divide by 0. We can't do that. So if x equals 2, that would make the denominator 0. Therefore, we have to say x cannot equal 2. This polynomial still looks pretty complicated to me, though. We know these two things are true. I'm going to put those over to the side there. Let's see if we can simplify the polynomial sum. There's nothing that I see right now that's a common factor between the numerator and the denominator, but I do remember how to factor the numerator. It is a difference between two cubes. It is actually x cubed minus 2 cubed. And we know that will factor into x minus 2 times x squared plus 2x plus 4. Remember our SOAP that we always use? Now I can take the factored form of my numerator. It is still over x times x minus 2. And now that I have it factored in both the numerator and the denominator, I can see that my x minus 2 is a common factor of each of those, and it cancels. So finally, I can express my polynomial in a simpler form here. There is no common factor now in the numerator and the denominator, so I have simplified it as much as I can. However, I do still have to remind everyone that x cannot equal 0 or 2. Notice in its current form, it doesn't matter if this x in the denominator is 2. You can divide by 2. But this has to be completely equivalent to our original form, in which if we put a 2 in here, we'd get what? 4 minus 4 or 0. So we have to include this information for what x cannot be, either in the final form or in the original form. Time for another example. Here's another example. So looking at this example, what would make the denominator equal to 0? Well, the answer, just looking at it there, is 3. We can get that by adding x to both sides, which means that 3 equals x, or x equals 3. But remember, that is what we do not want. We do not want x to equal 3. So x cannot equal 3. Now that we have made a note of that, let's take a look at how we could simplify this polynomial ratio, or ratio of polynomials. Well, we could factor the top, right? X squared minus x minus 6 would factor into a negative 3 as the second term in the first binomial there, and a 2. So x minus 3, that quantity, that binomial, times the binomial x plus 2, would give us our original polynomial, happens to be a trinomial, divided by 3 minus x. Are there any factors in common? The answer is actually yes. But these two, x minus 3 and 3 minus x, are very different things. However, here is a really neat technique that you can use. 3 minus x. There's our binomial. What would happen if we divided or factored a negative 1 out of each of those terms? So if we divided 3 by a negative 1, we'd get a negative 3. And if we divided our negative x by a negative 1, we'd get a positive x. And we could change the order of those to make it positive x plus a negative 3, or x minus 3, which just happens to be what we have in the numerator. Factoring out a negative from an expression is a very handy tool, and here are some other examples of how it works. In fact, once you notice the pattern, you don't actually need to use this step for either of these. Once you see that if you divide out a negative 1, it leaves the subtraction there as the operation, but it switches your first and second terms. See how that happened? So you can just move to the next step. However, remember that you have to still keep this negative 1 in there. It does not disappear. It is still there. So let's just make these examples a little bit smaller and keep them nearby and return to the problem we were working on originally. By what I just showed you, using that technique, we can change the denominator to negative 1 times x minus 3. And now x minus 3 goes in here one time, it goes into the denominator one time, and our simplified version of the original ratio of polynomials becomes negative 1 as a denominator with x plus 2 in the numerator. Can we work through that a little bit more, get rid of that negative 1? Yeah, we could bring the negative into the numerator because that's equivalent. And we could then make this negative x minus 2. Is there anything in the expression negative x minus 2 that x cannot be? Will any value of x give us a non-real number or no number at all? Is there any way we divide by 0? No. But once again, in the original expression, we had 3 minus x. X does not equal 3. So negative x minus 2 is the simplified form of our original ratio where x does not equal 3. Time to move on. You have worked with fractions, and you have added and subtracted fractions quite a bit, even learning how to subtract one fraction from another when the fractions have different denominators. And just as you see this problem worked out here, where we go from fractions with different denominators to fractions with the same denominator, and then we can subtract. We will subtract one ratio of polynomials from another ratio of polynomials using the same techniques. Now, simply by looking at the second of these two ratios, over here, I can see that a 2 substituted for x would give me a 0 in the denominator. So I already know that x cannot equal 2. But in this denominator right over here, I'm not so sure. So I'm going to go ahead and factor both of those denominators. That's going to make it easier for me to find a least common denominator anyways. So everything that's up there is equal to, well, there's no common denominator in that numerator, so I cannot factor it. But I can factor the denominator this way. And my second denominator actually factors as a difference between two squares. So there it is. And now I need to find a least common denominator. So an LCD, let's see, one of my denominators is x minus 2 times x plus 1. The other is x plus 2 times x minus 2. So my LCD, which I'm actually going to write down here, is x minus 2 times x plus 1 times x plus 2. So now we need to look at what we need to multiply each of those ratios by to get a least common denominator. The only factor missing from the denominator on the left is the x plus 2. So I will multiply that ratio by x plus 2 over x plus 2. I will multiply the other one by what's missing in the denominator, which is the x plus 1. And I'll do that in the numerator and the denominator. Now the thing to remember about ratios or fractions is that the numerator is already in a grouping symbol. That fraction bar serves as a grouping symbol, but it helps to write parentheses in there to remind us of that. Because what I now have here is this binomial, x plus 2 times this binomial, 2x minus 1. We're going to have to use the distributive property of multiplication over addition in order to work that out. And we'll have to do the same thing for the second numerator. But right now, I'm just putting both of those numerators over my least common denominator. Now, I still have this subtraction sign in between the two fractions or ratios, so it must remain there. So I have that negative, subtracting from that 2x times x plus 1. Now, it would be nice if there were a common factor in each of these terms, but there is not. So surely there's some way we can simplify this further. And by the way, that's equal to that, and this is going to be equal to, we're going to have to make it look a little more complicated maybe, by actually doing the distribution. Binomial times a binomial, we often remember that by talking about FOIL. First, that's 2x squared minus x plus 4x minus 2. First outer, inner, last. But then we come to this subtraction sign, and we are subtracting everything that follows. So we need parentheses here still. We're going to distribute 2x to the x to give us 2x squared, and then 2x times 1 will give us a positive 1. I went a little crazy there with that 2, didn't I? There we go. 2x squared plus 1, and I can pull that parenthesis in closer. Now, why did I leave that parenthesis there? That pair of parentheses? Because that negative has to be distributed to everything in that what was formerly a separate numerator. So I'm still going to be using distribution. I'm going to distribute the negative, which can be thought of as a negative 1. All right, I need some more room again. Okay, this is going to be 2x squared minus x plus 4x minus 2 minus 2x squared minus 1 all over the denominator. And then I'm just going to quickly cut to all of the like terms in the numerator being added. Now, you may be able to see this right away, but if not, you can always factor again in the numerator, but I've already seen that nothing will cancel, that it is in the simplest form at that step. But let's remember, if we're expressing that as our answer, we have to see if there are any values x cannot be. So going back to the going back to the beginning of the problem, we see that when we factored each of those denominators, we had x minus 2, x plus 1, x plus 2, x minus 2. None of those disappeared completely. Okay? We still have we have an example of every one of those factors remaining in our answer. We have x plus 2, we have x minus 2, we have x plus 1. There were no other factors in the original. Nothing has canceled from the numerator and the denominator. So we can just look at our final expression here and say this is where x does not equal 2. Actually, we usually put it in order from smallest to largest. So x cannot equal negative 2, negative 1, or 2. Because if x is negative 1, this will be 0, and 0 times anything is 0. If x is negative 2, this factor will be 0, and 0 times anything is 0. And likewise, if x is 2, this factor will be 0. So there we have it. Does it matter if x is 3? That would make the numerator 0. That's okay. We can deal with the numerator being 0. That would just make the entire ratio equal to 0. And that's an actual number. So this is the first video of 2 that I'm going to be preparing for you, so you can take a break before you watch a video about what you do if you have complex fractions, remembering that this is the same thing as 1/3 divided by 1/5, which is the same thing as 1/3 times 5/1, which will give you 5/3. However, we are not going to refer to this as a complex fraction. We're going to refer to it as a complex rational expression because we can. See you in the next video. Take a break.